Hello everyone, my name is Sahil and the video is about crosswalk guidance for low vision people. Abstract. Visually impaired people find traveling outdoor inconvenient due to the lack of ability to navigate and recognize hazards and obstacles. Multiple techniques are implemented over the years such as wearable devices to assist people to detect obstacles to avoid unwanted consequences. Zebra polyline crossing are used in many countries in the world including USA, China, India and all follow same pattern made of distinct white stripes on the road. Using adaptive thresholding and taking spatial variation and illumination in account, bright stripes of crosswalks are extracted. A main operation of this system is self-localization, the estimation of the user's location relative to the crosswalks in the current traffic intersection. A mobile application with the help of built-in camera will allow the people at the signalized crossing by providing them orientation and signal information using adaptive extraction and consistency analysis. The output will be a voice prompt which will help visually impaired people to align and walk along the crosswalk. So below are the images of different type of crosswalks in different countries. And on the right there's a difference shown between ordinary crosswalk and a polyline crosswalk. Table of contents. So we have introduction and problem definition, the previous work done on the topic, what are the limitations and tackling the limitations, the real-time crosswalk detection using neural networks, adaptive thresholding, candidate analysis, challenges faced, the future and conclusion, and at the end, bibliography. So we'll start with introduction and problem definition. So for low vision people has limited visual information which can restrict them from crossing the intersection without proper guidance from a guide dog, cane or a helping hand. Also at times it is hard for them to locate the push button in order to use it and might deviate from them from the original route. An application supported by well-built computer vision libraries help visually impaired people across the signalized intersection with ease. The mobile camera will act as a main source of input for the system and by analyzing the environment and audio output will help user navigate and guide them how and when to cross the road. The user interface is as simple as a touch or double touch to a screen along with the information provided by the GPS and using computer vision and deep learning techniques and algorithms such as edge-based, grayscale, and bright stripe-based algorithm, it becomes easier for low vision people to cross the intersection. The system accuracy can be increased by collecting more and more training data that will help machine learn and act according to the surrounding environment. So below is the example that shows the difference between what a normal people see versus a low vision people, and as you can see on the right, it's kind of hard to detect the crosswalk for low vision people. So the previous work on the topic, edge-based algorithm. A typical crosswalk has bright stripes like white and yellow and a dark background which are parallel and form a perfect edge which are differentiated using computer vision libraries such as OpenCV. Using random sample consensus algorithm and any canny edge detector, the long edges in a crosswalk are extracted. As the algorithm name itself suggests, it works best only for a straight line crosswalk where it is not valid for a polyline crosswalk. So what is RANSAC? RANSAC stands for Random Sample Consensus and is algorithm proposed by Fischler and Bowles to cope with the large proportion of outliers in the input data using an estimation approach. The algorithm takes minimum number of observation to estimate the model parameters and generate candidate solution. Bright stripe based algorithms. By extending RANSAC functionality and based on maximally stable external regions, the algorithm works well under different light illuminations. Using ground segmentation, we can detect the crosswalk if we develop the relation between position of stripes and within the images. The processing an image takes extra few seconds when compared to above mentioned algorithms, but results are more accurate. So all the algorithms mentioned above has the limitations, and the limitation is that they work on a particular scenario, assuming that users are well aligned with the crosswalk. What if users are not well aligned? And in practical, crosswalk may represent different orientation, and in that case, it is hard for the system to detect the appropriate path. The crosswalk at distance are hard to detect, which is one of the main limitations. So in next we'll face the limitations and we'll come up with a system that overcomes the limitations. To understand the problem in detail, below given images is an example of different scenarios of a crosswalk navigation A, B, and C. So the points in green, the points in green A, B, and C are the position of the user, while the yellow line is the field of view. In order to tackle the limitation, the system should detect the crosswalk from distance, which will help the user to align well with the crosswalk. Recorded voice prompts provide user with the signal and orientation information. Safety of user is one of the main concerns while developing the system and should deliver low false alarm. The system must work in a real time to give the best experience. This is a typical scenario of a crosswalk detection, and the images are captured at point A, B, and C are shown on the left. A, B, and C. Next, we move on to real-time crosswalk detection using neural network. So the detection algorithm has four basic steps. To detect the crossing, the algorithm proposed is shown in figure below figure 3. Using the neural network, threshold is determined for adaptive thresholding, which helps extract dark connected components from a grayscale image. A stripe in a crosswalk is considered to be the subset of the image where any 2 points in the subset are connected. The extra component in the input, such as background that includes sky, trees, and other surrounding objects, are eliminated by analyzing geometrical properties. By consistency analysis, important features are selected, which from a crosswalk and also the position of the orientation of the path are also obtained. So this above is the flowchart that shows the adaptive candidate extraction and consistency analysis. The lateral images A to D represent the results of the corresponding procedures. So on adaptive thresholding, it gives a binary image of black and white. Candidate analysis gives the edges based on the in the picture, and consistency analysis and also removes the obstacles from the obstacles from the images. So next we move on to adaptive thresholding. Adaptive thresholding based on neural network. Acquired color frames from the camera are transformed into grayscale images. Since the brightness of the crosswalk is used in binary thresholding and the HUE of the crosswalk could be neglected. The fixed thresholding algorithm has a poor performance because threshold is predetermined and does not vary with diverse elimination. Here, the adaptive thresholding is adopted to address the issue, where the threshold is not fixed but determined by the input of the image. An artificial neural network is commonly used model to deal with adaptive binary thresholding problems. So in this, we have used the three-layer feed-forward neural network to express the relation between a grayscale image and a binarization threshold. As shown in figure 4, the neural network is comprised of input layer, the hidden layer, and the output layer. Each neuron in the hidden layer is directly linked with the neuron in the input and output layer. The input layer, suppose X has X1, X2, X3, Xn neurons, and receive the downsampling grayscale image. The original grayscale image is resampled to a tiny image as shown in figure and unfolded to form vector X. So this original image is using the image decimation. It forms a tiny image and all the pixel by pixel values are fed to x1, x2 and so on till xi neurons, and then all these neurons are connected to the layer 2 neurons, and in turn all the neurons in layer 2 are connected to layer 3, which gives the output as t, and the t output is a binary image. So thereby the suitable threshold t is determined the product of the possibilities and the threshold values. So having determined the threshold t, we can carry out the binary thresholding of on the original grayscale image and get the binary image. The bright pixels are grouped to form connected components. So here the output is t, which is the threshold, and all the pixel values above a certain threshold value gives us a color black, and all the pixel values that are below a threshold t gives you the white. So it is made up of two colors, black and white, and it's called binary image. So next is candidate analysis. This is basically used to get rid of the noise from the picture. The geometrical properties of the candidates are analyzed to remove the undesired candidates generated by the adaptive thresholding. The size, orientation, and convexity of each candidate are examined, and only those candidates can conform to form all the criteria and are retained. In addition, candidates with simpler geometrical shapes and properties are merged, which restores crosswalk stripes separated by pedestrians or other objects. The size filter is designed to eliminate enormous and tiny candidates, such as bright pebbles and the sky. It does not aim to select crosswalk stripes from candidates exactly. Therefore, the upper bound and the lower bound of the filter could be determined empirically. The maximum and the minimum size of candidates are defined as the size of the maximum and minimum candidates is equal to some constant into h, which is height, and w as in the width of the input frame. To avoid the eliminating prospective crosswalk stripes, the interval of the upper bound and the lower bound is intentionally enlarged. So this image A is after the adaptive thresholding and with noise, and on consistency analysis, it gives you B, which is less noise and is only white and black zebra crossing. And the same is for D, it has a lot of noise, and after the analysis, it gives you only the black and white stripes on the crosswalk. So, what are the challenges that I've faced? One of the main challenges faced is to collect the data that belongs to different environments consisting of different scenarios. Crosswalk detection from far distance is one of the main challenge. Pedestrian occlusion, low contrast crosswalk, various illumination, that is in pictures are clicked in the various environments, which has some are clicked in cloudy environment, some are clicked in sunny, while some are in dark. Limited resources of a portable device, that is the limited capability of a camera to click the pictures. Conclusion and future. The purpose of our system is to help blind people and visually impaired pedestrians align themselves properly to a crosswalk before crossing. The success of this system demonstrates the feasibility of implementing real time computer vision algorithms on the mobile phone despite its limited computational powers. After these steps have been taken, subject testing will be conducted to determine whether the system is usable, measure its performance quantitatively, and elicit feedback to see how the system can be improved. At a later stage, the system can also be augmented by additionally functionality, including the detecting the two stripe as well as the zebra crosswalk, detecting walk lights, pedestrian signals, and or traffic lights, and monitoring the pedestrian's path to prevent him or her from straying out of the crosswalk while traversing it. So this is it. And the next page is about the references that I've used to make this website, and it has six references, and all majority of them are the article or the paper research paper published. And yeah, that is it. Thank you.